Okay, thanks, Vita, for that introduction. So I'll be talking about some of my work toward dedicated positron emission mammography and ultrasound-guided breast biopsy. So I thought I'd start out with a brief outline. So I want to first briefly touch on the motivation and really importance of biopsy-based diagnosis in breast cancer, provide an overview of current breast imaging methods and an alternative functional imaging modality, positron emission mammography, and then describe some of our system developments and results for PEM and ultrasound-guided breast biopsy toward improved spatial sampling in breast cancer. So as we know, breast cancer is the most commonly diagnosed cancer in women, and definitive diagnosis of breast cancer still relies on a breast biopsy. Interestingly, in a population of 1 million women that require a breast biopsy, 3/4 will have a negative biopsy result, meaning they may have had a possible unnecessary intervention or are at risk of a false negative result. In the remaining quarter with positively identified breast cancer, early detection and treatment will determine if they survive. So really, this is our clinical challenge to improve the detection and biopsy-based diagnosis of breast cancers to improve patient outcomes. So how do we approach our challenge? Well, this first involves screening that is highly sensitive and specific to detect early stage cancer. And when a suspect lesion is found, often this involves additional imaging to accurately localize our lesion. Then for conclusive diagnosis, we need an intervention that is highly accurate and efficient to target our lesion to assess for pathology, diagnosis, cancer staging, and ultimately treatment planning. And most commonly, this involves an image-guided needle biopsy to both localize and spatially sample these lesions. So to overview conventional breast imaging and guidance methods, our most common method is X-ray mammography. However, this modality is strongly limited in women with dense breast. Glandular and fibrotic tissues can attenuate X-ray photons, which limit the intensity and soft tissue contrast to detect these abnormalities. And critically, this impacts 40 to 50% of women. So for these women, secondary imaging methods are necessary. So ultrasound is an alternative which provides real-time detection of physically palpable breast lesions, but is limited in both sensitivity and specificity. Furthermore, its detection is reliant on clinician ability to detect between benign and malignant lesions. An alternative and gold standard method for women with dense breast is currently MRI. And although MRI has a very high sensitivity, it has a relatively low specificity due to the enhancement of both benign and malignant lesions, which may induce many false positive results. This may contribute to unnecessary intervention in this population of women. An alternative to these conventional anatomical methods uses a functional imaging approach. And the key idea here is to combine highly specific molecular tracers, such as FDG, and radioactive isotopes, such as fluorine-18, with high resolution imaging components. This allows us to image increases in glucose metabolism or functional activity, which is a hallmark of cancer. And in positron emission tomography, or PET, this involves our annihilation coincidence detection of gamma rays using a whole body PET detector ring. But a critical challenge here is that these methods have a limited sensitivity and spatial resolution, which is ultimately not sufficient for detecting early stage breast cancer. To address these challenges, breast-dedicated PET, or positron emission mammography, systems have been developed involving two planar detectors rather than a whole body ring to image the breast. This enables two advantages. First, it allows for an enhanced sensitivity due to the closer proximity of the detectors to the radiation source, and also lower effective radiation doses due to the reduced tissue thickness during imaging. So to address our clinical challenge, improving detection, especially in high-risk women with dense breasts, requires better imaging, and dedicated PEM provides this potential and capability for more sensitive and specific tumor detection independent of breast tissue density. And to provide conclusive biopsy-based diagnosis, we need to integrate an intervention. However, PEM provides no anatomical context, and this limits visualization for needle guidance and targeting. So to accomplish this, to address these challenges, we propose combining PEM with an ultrasound-guided needle biopsy method. And to accomplish this, we require methods to integrate ultrasound to PEM localization workflow, and additionally accurate and precise methods to remove uncertainties while targeting these breast lesions. And therefore, the aim of my work is to develop and validate a system integrating targeted ultrasound-guided needle biopsy with high-resolution PEM localization to improve the spatial sampling in these breast lesions. So we developed a Mechatronic guidance system, which integrates ultrasound and a biopsy intervention designed to operate with an advanced Radialis PEM imaging system developed by our collaborators. And the system was built, it was mounted to a medical cart to interface with custom software modules for guidance. And for the purpose of visualization, our upper detector plate is removed in our left image to illustrate our accessibility in between these plates to perform biopsy. Then to describe our system components in detail, our system contains a clinician-operated counterbalance stabilizer, angle sensing rotary encoders at each joint for tracking 3D position in space, and electromagnetic brakes at each joint for locking our system in place for biopsy. Our end effector is a biopsy device, which contains a integrated linear ultrasound transducer and also a core needle biopsy gun, which is focused on a remote center of motion. So forward kinematics of motion were implemented to our system, and encoders were used to determine its 3D position and orientation in space. This is an adapted screen capture in world coordinate space from custom guidance software. To evaluate needle tracking, we machined a detector plate with dimensions comparable to our PEM system and removable blocks in known locations. And to simulate targeting, we replaced our needle with a machined extension at its remote center of motion to fit into these divots. With this, we could register our guidance arm coordinate space to our PEM image coordinate space relative to this detector plate, with 8 non-collinear calibration fiducials positioned on the periphery, illustrated in red, and using landmark-based registration. Then validation was performed within a relevant central region of the simulated plate, where additional fiducials were distributed with select points illustrated in yellow around the relevant central region of the detector plate to simulate the positions of PEM localized breast lesions. And finally, here we can compare our corresponding pairs of measured positions obtained from the transformation in our software and its actual position in 3D space. When our system was registered, we optimized our visualization module for user guidance in the PEM image coordinate space, which is illustrated here on the left panel, to target simulated lesions localized with PEM, but also corresponding to physical targets embedded in tissue mimicking Agar breast phantoms. And here we can target in 3 spatial dimensions to a select target lesion indicated as our red circle, where our blue and green crosshairs represent the real-time in-plane position, and our slicing cross-plane represents our z-axis position. Then, when in close proximity to our target, our software automatically switches to a 2D view for in-plane positioning of the remote center of motion, where the system can be locked to perform biopsy. And here, 3D positioning error between our actual target position and our position displayed in the software was quantified. Then our ultrasound transducer can be extended to the surface of the phantom, and needle guidance can be performed in real time. We quantified the needle targeting error, which was the distance between the manually segmented needle center line and the target center position. And finally, we performed these procedures 20 times in lesions 4 millimeters and 6 millimeters in diameter and height, and quantified both the positioning and the needle targeting errors. So our fiducial registration error in our calibration demonstrated an excellent sub-millimeter registration of 0.37 millimeters, and our following target registration error within the central region of the plate was slightly elevated with a mean of 0.70 millimeters. And furthermore, to evaluate directional trends, principal component analysis was used to plot a 95% prediction ellipsoid, which is essentially a volume centered on the mean 3D TRE, such that any future observation observation is expected to have a probability of falling within this volume. And here we see an isotropic distribution, and we observe no significant deviations from our centroid in 3D space. Additionally, our error volume is equivalent to a sphere with a radius less than 1 millimeter in diameter. In our phantom studies, we successfully targeted 20 lesions in our mock biopsy procedures and performed in 4 millimeters and 6 millimeter diameter targets, as indicated by our target being identified in our core sample. And the 3D root mean square error was 0.84 millimeters, with component errors 0.64 millimeters in plane and 0.2 millimeters cross plane. And our directional trends in plane are illustrated in this 95% prediction ellipsoid, showing a very small positive bias in user positioning. And within 95% confidence, these in-plane targets, approximately 1.04 millimeters in radius, can be targeted with 95% confidence. Finally, needle targeting error in our post-fire ultrasound images were quantified, which includes components of registration and positioning error, and this was about 1.08 millimeters. Using a one-sided confidence interval, targets 1.32 millimeters in radius can be sampled with 95% confidence. So finally, we described a guidance system for targeted ultrasound-guided breast biopsy under high-resolution PEM localization. And in this work, we implemented and demonstrated real-time needle tracking capability, our registration and breast phantom testing with a simulated PEM detector plate reflect a proposed clinically feasible workflow. And our phantom studies show accurate 3D needle guidance and positioning with an overall error less than 1.4 millimeters. And ultimately, the impact of this work is that our system will provide the ability to target not only small early stage breast lesions, but also higher grade breast lesions with multiple regions of variable genetic profiles, which can be detected and localized with PEM imaging. So finally, future work will integrate our developed system with the Radialis PEM imaging system and evaluate its accuracy to localize the target position lesions for sampling, and additionally to perform additional phantom experiments using radioactive inserts to evaluate this intrinsic registration accuracy between the fused in-plane PEM and ultrasound images to perform biopsy. So finally, I'd like to thank my supervisor, advisory committee, lab, and funding sources in which this work would not be possible. And thank you for your virtual attention and time.